Okay, if you've spent any real time with generative AI, you know the feeling. The models, brilliant. The output, often amazing. But the waiting, watching that cursor blink.
Yeah, token by token, it's often just agonizingly slow and expensive too when you factor in compute costs. High latency is like the default experience.
Exactly. So today we're looking at a really interesting article proposing a solution. It's called KLM, Continuous Autoregressive Language Models. And, okay, let's unpack this. The core argument here is that this slowness isn't just bad code or servers. It's baked into the architecture.
That's right. The standard way these things work, autoregressive models, they have this built-in speed limit because they generate, well, one tiny piece at a time.
So the article argues it's time for a fundamental shift.
Precisely. They're not just tweaking things. This isn't another fine-tuning trick. They're changing what the model actually predicts at each step, moving from next token prediction to something they call next vector prediction.
Vector prediction. Okay. The mission is clear. Cut down that latency, reduce the cost, basically make these models much more efficient by taking bigger steps.
Exactly. Widening the semantic step, as they put it.
All right, before we get into the solution, let's just quickly baseline the problem. Remind us, what exactly is an autoregressive model, and why is the thing that makes it work also its biggest speed bump?
Sure. So autoregressive models are powerful because they predict the very next piece of output, the next token, using everything generated right up to that point.
Like a feedback loop.
Exactly. A very tight, very stable feedback loop. Output at step T feeds right back in to decide step T plus 1. That's how you get coherence, how the model, stays on track.
But that stability has a time cost. A big one.
A huge one. Because the next prediction absolutely depends on the current one. You can't really generate the steps in parallel. You can run multiple prompts at once, sure, but for a single output, it's step by step by step.
So the longer the answer, the longer you wait.
Yeah.
It just scales linearly.
That's the hard limit.
And the article introduces this idea I found really insightful. Semantic bandwidth. It's not just about the number of steps, is it?
No, it's deeper than that. It's about how much meaning each step actually carries. Tokens, the individual units these models usually predict, are informationally quite thin.
How thin?
Well, with typical vocabularies, they figure each token carries maybe 15 to 18 bits of actual semantic information, which isn't a lot when you think about complex ideas.
So the analogy they used, moving information through a straw.
Yeah, that one really lands. You could have this massive model, a huge brain, but you're forced to communicate its thoughts through this tiny little straw, one sip at a time. Writing a paragraph means hundreds of sips.
And that's why optimizing inference is such a massive deal for everyone using LLMs.
Absolutely. It's a fundamental bottleneck.
Okay, so if the straw is too thin, KLM's idea is use a bigger straw. Tell us about this next vector prediction.
That's the core idea. Instead of predicting the next discrete token ID, KLM predicts a continuous vector. And this single vector is trained to represent or stand in for a whole chunk of, say, K tokens.
K tokens, okay.
So the model predicts this dense vector, and then a decoder translates that vector back into the actual K tokens for the output.
Right, so if K is, let's say, 4, which they test a lot in the paper, you've immediately cut the number of prediction steps by 4.
Potentially, yes. 4 times fewer autoregressive steps.
That seems like a massive speed up. But, okay, my skeptical hat is on. If it's just about bundling tokens, why didn't this work before? What's the catch? What makes it stable now?
That's the key question. It's not just bundling. People have tried variations before. The trick is doing it without the model just, losing the plot after a couple of steps. Coherence and fidelity are the hard parts.
So how does KLM maintain that coherence?
It still uses the history. The autoregressive principle is still there. But the crucial difference is where that feedback loop closes. In a classic model, you predict a discrete token ID. Then you look up its embedding, turn it back into a vector, and feed that into the next step. The loop goes vector space, token ID, vector space.
Right.
KLM keeps the loop inside the learned latent vector space for longer. It predicts the next vector based on the history of previous vectors. It only decodes that vector into actual tokens at the very end of the chunk boundary.
Okay, so the core calculation stays in this richer, continuous space between steps.
Exactly.
So the analogy holds then. It's like drafting 4 words or a phrase at once when the context allows, rather than strictly one word at a time.
That's a good way to think about it. You still check the past, but you take a bigger stride forward.
Yeah, and you mentioned a hardware benefit. Right. Fewer expensive operations.
Yes, absolutely. Every single autoregressive step requires memory writes and, critically, a full pass of the attention mechanism over the entire history so far. Attention is computationally very expensive.
The dominant cost, usually.
By far. So if you cut the number of steps by a factor of k, you cut the number of these super expensive attention calculations and memory accesses needed for the full output. That's a direct path to faster inference on existing hardware.
Makes sense. But making this work sounds non-trivial. The article dives into a specific three-part toolkit for the CALM architecture. These seem like the crucial engineering pieces.
They really are. CALM isn't just the vector prediction idea, it's this whole engineered system designed to make that idea practical and stable.
Okay, let's break it down. Part 1, the high-fidelity autoencoder.
Right. This component is vital. Its whole job is to take that chunk of K tokens, compress them down into that single, dense, latent vector, and this is key, be able to reconstruct the original K tokens almost perfectly from that vector later on.
How perfect are we talking?
The paper mentions aiming for over 99.9% reconstruction accuracy. If the compression is lossy or the decompression introduces errors, the output quality degrades incredibly quickly. Gibberish follows.
So how do they make the compression so robust? Just train it really well.
It's more than just standard training. They use specific techniques like variational regularization and dropout. Basically, variational regularization helps ensure the learned latent space is smooth and structured. Meaning small errors in predicting the vector don't suddenly blow up into huge errors when you decode it back into tokens. It forces the model to learn representations that are resilient to tiny imperfections.
Got it. Okay, tool number 2. This is where the training changes fundamentally, right? Because predicting a vector means you lose the standard softmax output layer.
Correct. The softmax layer in traditional LLMs is what gives you that nice probability distribution over the entire vocabulary for the next token. You know, there's a 30% chance the next token is the 10% chance it's A, and so on. Standard training methods, like cross-entropy loss, rely heavily on those explicit probabilities.
And with a continuous vector, you don't have that list of probabilities anymore.
Exactly. You're predicting a point in a continuous space, not picking from a discrete list. There are infinite possible vectors, so you can't assign a probability to each one like you do with tokens.
So how do you train it then, if you can't calculate the usual loss?
They introduce what they call a likelihood-free generative head. It's based on energy-based models. Instead of predicting probabilities, it learns an energy function, where basically lower energy corresponds to better, more plausible next vectors.
And crucially, how does it generate the next vector during inference?
Critically, it samples the next vector in a single step. It's not an iterative process within the step. This is important. You don't want to trade the token-by-token bottleneck for some new, slow sampling bottleneck inside the vector prediction step.
Right. You want the whole step to be fast.
Okay.
And the third piece follows logically. If you don't have likelihoods, you can't use standard evaluation metrics like perplexity.
Precisely. Perplexity is fundamentally based on those token-level log probabilities. So they needed a new way to measure how well the model is doing.
Enter the BrierLM metric.
Yes, BrierLM. It's a different kind of scoring rule, one that works by comparing the predicted vectors to the actual ground truth vectors from the data without needing explicit probabilities. It operates directly in that continuous space.
But how do we know if it's a good metric? Does it actually track quality?
That's a fair question. They did work to validate it, showing that on standard models where you can calculate both, BrierLM scores correlate very well with traditional cross-entropy loss. So it seems to be a reliable proxy for model quality in this new continuous prediction setting.
Okay, theory and architecture are interesting, but let's talk results. The article includes a table comparing performance, and this really shows the trade-offs in practice.
It does. This table is pretty central to their argument. It compares standard transformer models, they label them S, M, L for small, medium, large, against column variants, specifically M, L, and XL, all using K4.
And they compare them on parameters, training compute FLOPs, inference compute FLOPs, and quality using that BrierLM score.
Right. Lower BrierLM means better quality.
So let's take a key comparison. How does the baseline Transformer S stack up against the CalM?
Okay, Transformer S has about 281 million parameters and gets a BrierLM score of 6.05. Now, the CalM model is a bit bigger, around 371 million parameters.
Oh, look at the quality and cost.
Exactly. CalM achieves a better quality score, 5.72 BrierLM, which is lower and thus better. And here's the kicker. It uses significantly less compute. About 44% fewer FLOPs for training 3.7 versus 6.6 trillion FLOPs.
And inference?
Also much better. 34% fewer inference FLOPs per generated token, 2.9 billion versus 4.4 billion.
That's pretty remarkable. You usually trade off quality for speed or pay more compute for better quality. Getting better quality with less compute, both for training and inference, that's rare.
It really is. It's that win on both time and money scenario that everyone wants.
And does this efficiency hold up as the models get bigger? What about the large ones in the table?
It seems to. If you compare the Transformer L, around 849 million parameters, with the Column XL, which is much larger at 1.82 billion parameters.
So more than double the parameters for CumXL.
Yes. But look at inference FLOPs. Transformer L costs 15 billion FLOPs per token. The much larger CumXL costs only 9.4 billion FLOPs.
Wow. So even though it's a vastly bigger model, potentially capable of more complex reasoning, it's still significantly cheaper to run for generation than the smaller baseline transformer.
That's the claim. It ties back directly to cutting down those attention passes. The cost per step might be slightly higher because the vector is denser, but you're doing k times fewer steps.
So the big takeaway from the results seems to be
That this k factor, the chunk size, acts like a whole new dimension for scaling these models. It's not just about more parameters or more data anymore. Increasing k gives you a new lever to pull, specifically for improving computational efficiency, reducing attention cost, and memory pressure per token generated.
okay, let's pivot to practical advice. If a team is looking at this thinking, maybe we should try this, what does the article suggest? How do you actually implement Callback?
Well, first step, pick your k. They suggest starting small, maybe K2 or K4. There's a trade-off.
What's the trade-off?
Larger K gives more speed up, but might hurt quality or coherence more, especially on tasks needing high precision. They suggest short-form chat might handle larger K, while something like complex code generation might need smaller K, perhaps compensated by a larger base model.
Makes sense. And obviously use BrierLM for evaluation since Perplexity is out. What about integrating it into the inference stack?
The big win is fewer steps means fewer attention computations, which means less demand on memory bandwidth per generated response. The advice is basically, LLM plays really well with existing optimization tricks like KV caching or quantization. Combining them can lead to very fast inference without needing bleeding-edge, specialized hardware.
So it potentially makes high-performance LLMs more accessible.
That seems to be the implication. And there's another interesting point about tool use or agents.
Ah, right, because agents often make step-by-step decisions.
Yeah. With LLM, each step now represents potentially a whole phrase or logical chunk. So the advice is to align your agent's decision points or tool calls with these chunk boundaries. One model step might now correspond to a more meaningful action or observation.
Which could maybe make agents less erratically chatty.
Potentially, yeah. More grounded actions per inference step.
Sounds very promising. But there's always a catch, right? What are the downsides or challenges mentioned?
The big one, and it's significant, is losing those easily accessible token-level log probabilities because you don't have the softmax output.
Right, we talked about that breaking standard training laws. Why else is that a problem?
It really messes with a lot of the modern fine-tuning and alignment techniques. Think reinforcement learning from human feedback, RLHF, or direct preference optimization, DPO.
How so?
Those methods rely heavily on comparing the probabilities the model assigned to the chosen output versus other possible outputs. They use those log probabilities to calculate rewards, to understand model confidence, to steer the model towards preferred generation styles based on human ratings.
And without those probabilities.
The standard RLHF preference tuning machinery just breaks. You can't easily compute the ratios or differences that drive the learning process.
So adopting COM isn't just a model architecture change. It forces you to rethink your whole alignment and fine-tuning pipeline.
Absolutely. You'd need to develop new methods, maybe new adapter layers or different objective functions entirely that can work in this continuous prediction space without explicit token likelihoods. That's a major research and engineering effort.
Okay, so wrapping up, COM looks like a clever evolution of the transformer. It keeps the core autoregressive idea for coherence, but speeds things up by essentially making the model predict bigger chunks of meaning vectors instead of tokens.
Right. And the key takeaway seems to be that this chunk size, KS, is a new powerful knob for optimizing inference speed and cost, and its benefits seem to compound with other techniques.
So final thought to leave folks with.
Well, the article hints that the future might not be about replacing autoregression entirely, but maybe evolving it further, having models that operate on even larger semantic units, maybe full ideas or concepts in intermediate steps. And that raises a really interesting, maybe slightly worrying question.
Which is?
If we move further away from discrete tokens and lose those token-level probabilities, how do we implement safety guardrails? So much of current safety tooling, content filtering, bias detection, even basic control relies on being able to inspect and score the output at the token level, often using those very probabilities from the softmax layer.
Oh.
If that layer disappears or becomes less meaningful, how do we ensure controllability and safety? We might need entirely new paradigms for safety that operate on these larger semantic chunks rather than individual words. That's definitely something worth thinking about as we chase ever more efficient models.